All right, hello guys. Sorry I am not in class today, but we want to get things going here and get you ready, make sure we're totally 100% ready to go for our IMF quiz later in the period here. So the first thing I'm going to start off with today is I'm going to draw out specifically the flow chart on how to identify the IMFs that are present in a molecule. So if you haven't noticed, I've basically taken the same steps every single time. So I'm just going to make sure I'm just super deliberate about drawing that out for you. So first things first that we have to accomplish is we have to draw a Lewis dot structure for every molecule that we're looking at. So we got to draw a Lewis dot structure out because we got to look at, because then we have to assign, right, the Vesper shape. Right, so if you don't have your Vesper chart out, you want to make sure that you have your Vesper chart out as well. If you can't find yours, well, there's another copy on Classroom, or if you're in person, there's a hard copy of the Vesper chart available for you in the front of the classroom. Okay, so once you look at the Vesper chart and you assign the Vesper geometry, then you got to decide, okay, is it symmetrical or is it not symmetrical? So if it is symmetrical, right? If it is symmetrical, that means that that molecule is nonpolar. Okay, you got to consider the 3D shape, right? You got to consider the 3D shape. So if it is symmetrical and it's nonpolar, then that means that the only intermolecular force present are London dispersion forces. So London LDFs only, all right? If you are symmetrical, because you are nonpolar. Now, if you are asymmetrical, means that you are not symmetrical, that molecule that you drew is not symmetrical, then that means that molecule is going to be polar. Okay? So at this point, now we have to make another another decision or identification, more or less. Okay, you want to look and see, all right, does it have hydrogen? Okay, and if those hydrogens, are they connected to a nitrogen, oxygen, or fluorine? So if there is no hydrogen on it, or the hydrogen are not connected to the phone to a fluorine, an oxygen, or nitrogen, then that molecule has London dispersion forces and dipole-dipole attraction only. Okay, because it's polar, it has dipole-dipole attraction, but because it doesn't have a hydrogen that is attached to a fluorine, oxygen, or nitrogen. All right, if it does have a hydrogen attached to a fluorine, oxygen, or nitrogen, it can dial up. It can phone another molecule and form some hydrogen bonds. Okay, remember, hydrogen bonding is just an attraction. Hydrogen bond, the name is awful. Okay, so if it has that hydrogen attached to an FO or N, it has LDFs, dipole-dipole, and hydrogen bonding. Okay, so it's got all those. All right, so that's our flow chart. That's essentially what we're using there, right? So we got to draw our Lewis dot structure, assign a Vesper shape, decide if it's symmetrical or not. If it's symmetrical, it's nonpolar, London dispersion only. If it's asymmetrical, it's a polar molecule, so it has dipole-dipole, but it's just a matter of, okay, if it's got a hydrogen that's attached to phone, then it's got all three. All right, so there's our IMF flow chart. So we're going to be using that. So you're going to need your periodic table and your Vesper chart out. And to review, I'm just going to go over a few of the problems that we had on the homework, the online homework, the UT homework. And they're the ones that kind of tripped us up a little bit more. All right? So here we go. So I'm going to start off with Number 5. Where's the answer? Okay, going to start off with number 5 here. And let's take a look at CO2. So they want to know what are all of the intermolecular forces that are responsible for the existence of dry ice. Okay, CO2. All right, well, we got to draw CO2. So we're going to draw a Lewis gas structure for CO2. Like a carbon, we have 1 carbon. And bring 4 electrons. We have 2 oxygens. Each bringing 6, so that's 12. So the total is 16 electrons. Carbon in the middle. Oxygen, oxygen, and then bond them out. So we minus 4. We have 12 electrons left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we made the oxygens happy. Each of them have 8 electrons. Put the carbon in the middle. Has only 4, and we got to make it up 8. So we need to share a few more electrons and make some double bonds because we are out of electrons to add to our molecule. So I'm going to steal this pair of electrons from oxygen on the right. I'm going to steal a pair of electrons from the oxygen on the left. Okay, draw a double bond in. So there we go. We've got carbon now is 2468. Each oxygen is 2468. So we're good. All right, so what's the Vesper shape here? Yes, it is linear. Okay, this is linear. This guy's symmetrical. All right, so now we're on our flow chart. Is he symmetrical? Yes, it is symmetrical. This has symmetry. Right, since it has symmetry, that means that it has LBFs only. Okay, and London dispersion forces only in this molecule. So solid dry, and the reason why they call it dry ice is because when the CO2, it doesn't melt. It actually just goes right from the solid to the gas because there is such small attraction between each carbon dioxide molecule that it just evaporates and it sublimates, I should say. Sublimation is going from a solid to a gas, just like that. So that's why it's dry. It doesn't form a liquid. Okay, so that's why it's dry. All right, very good. All right, number 6 here. All right, which one of these will have the largest boiling point? HCl or HI? All right, draw the Lewis dot structure for each. HCl, HI. Okay. Both these molecules very similar to one another. Okay. Okay. Are they symmetrical? No, they are not. Okay, so both have LBF, right? Because every molecule that has mass is LBS. And both have dipole-dipole attraction because neither of them are symmetrical. They have hydrogens. Is the hydrogen attached to a fluorine, oxygen, or nitrogen? No, it is not. So they do not have hydrogen bonding. So they have the same intermolecular forces present. So recall that more IMFs, right, equal higher boiling points, right? Because remember, to boil, you need to break free of the attraction, right, that you have to the other molecules around you. If you have more attractions to the molecules around you, it's going to take more energy, more temperature in order to turn from a gas or from a liquid into a gas. All right? So what we want to look at, are each of these guys polar? Yes, they are polar. both chlorine and iodine are both halogens. Okay, so these are going to be pretty polar in terms of their bonds. So, but they're going to be close. All right, so the polarity here is fairly close. That's an ugly arrow. Okay, so both are polar, but pretty close in terms of their polarity. Right, now when we look at the LDFs here, though, this is where the difference is. Okay, so you might recall, okay, these guys are very different in terms of their strength of their LDF. Remember that the strength of the LDF is related to mass. Right, so these guys are very different in their mass. Okay, because the strength of LDFs are in the mass. So which has stronger London dispersion attraction? Which one has stronger LDFs? Yeah, HI does, right? Why is that the case? Well, it's about 4 to 5 times more massive than HCl. Right? If you look at the periodic table, iodine has got a mass of like 129, where chlorine has a mass of about 30, 35. Okay, so that's about 4 to 5 times more mass. That's a pretty significant difference. So that's where the difference lies. Okay, so the one that would have the largest boiling point is going to have the strongest intermolecular forces. So dipole-dipole, both of them have that attraction, both are pretty close. But HI will have a much stronger LDF attraction than HCl. So HI will have the higher boiling point. Okay. All right, let's take a look at number 8. Oh, man. Okay, with number 8, all right, we're looking at propane and propanol. So propane, you might recall, is the gas that is in your grill, right, out on your deck or your back porch or whatever, okay, or in those little green canisters. If you've ever been camping or you used a lantern, a gas lantern, those little green canisters are filled with propane. If you shake that propane container, you can feel it slosh around in there. It's a liquid, okay, but when you open the valve, it's a gas. So it boils off. So when you release the pressure there, the molecule actually boils off. The propane is boiling off. Okay, so let's take a look at which one here. Propanol or propane is going to have a lower boiling point. So in a substance like this, if I were to give you the substance on your quiz, I would give you the Lewis dot structure. Okay, so for example, and these are organic molecules because they have carbon as their base. So, and they tell you how many hydrogens are attached to each carbon here. So we have, in the first one, we have 3 hydrogens and one carbon. So CH3, it's attached to another carbon with 2 hydrogens, CH2. And then it's attached to CH3 again. So remember, the carbons all have to be attached to one another because hydrogens can only form one single bond. So they are terminal. That you can't build off a hydrogen. All right, so there's propane. And similarly, if we draw propanol, okay, CH3, CH2, CH2, OH. Okay, so there's the Lewis dot structure for propanol. All right, so if I look at propane here, let's start with propane, and we check out that molecule, okay, so we have in the first one we have 3 hydrogens and one carbon. So CH3, it's attached to another carbon with 2 hydrogens, CH2. And then it's attached to CH3 again. So remember, the carbons all have to be attached to one another because hydrogens can only form one single bond. So they are terminal. That you can't build off a hydrogen. All right, so there's propane. And similarly, if we draw propanol, okay, Is that molecule symmetrical? I try to cut it down the middle. Try to cut it side to side there, right? This guy has symmetry. Okay, it is symmetrical. So this is LDF only. Okay, only one in dispersion force is there for propane. For propanol, so if you try to cut it down the middle, like perpendicular, right, or ironically there down the middle carbon, so one side you got the CH3 and the other side you got the CH4, right? So this guy is LDFs, and it's dipole-dipole because it does not have symmetry. And then finally, both of these molecules have hydrogen, right? But propanol is the only one that has hydrogen bonding because it's attached to this oxygen here, right? So this guy also has H bonding. Okay. So there we go. So propane only has LDFs, the weakest intermolecular force, and propanol has LDFs, dipole-dipole, and hydrogen bonding, all three of them. Okay, well, if we just look at the first question, I'm only going to deal with this first part of this question. Okay, I'm not going to worry about that part. We would expect propane to have boiling point, higher or lower boiling point than propanol. Lower. Propane's going to have lower because it only has LDFs. It's the weakest intermolecular force. That is it. Okay. All right, final example here. We're going to do number 9. Now I'm going to change number 9, the question up just a little bit. And I'm going to rank the following compounds in terms of boiling point. Okay, we're going to look at them in terms of boiling point. We're going to rank them from highest to lowest. And now look, I'm not asking you to look up a single boiling point value. I'm not asking you to do that. What I'm asking you to do is, can you deduce who would you predict to have the highest boiling point? Who would you predict to have the lowest, and so on? Okay? That's the thing here. Can we use a flow chart? Can we use our logical thinking skills to actually put these in order? I'm not asking you to go to Google and look up the boiling points for each one of these. It's just a waste of time. Okay? Let's try to use some logical thinking skills and go through a process to try to figure out what the answer is. All right? So let's go through each one of these molecules. I'm going to start off with H2O and work our way from left to right here. So H2O, right? I would hope that you guys can easily draw the Lewis dot structure for H2O. We have our bent shape here, and I would also hope that you would identify that, hey, this has LDFs, got dipole-dipole attraction, and it has hydrogen bonding. And I'm going to put H bonding times 2. Okay? It has 2 hydrogens that are attached to oxygen, and that oxygen has 2 lone pairs. So it could do that hydrogen bonding with another molecule. So it can form twice the number of hydrogen bonds. Okay? And let's take a look at NH3. I'll draw the Lewis dot structure for this. Just some. Okay, there we go. Obviously, this has LDFs. Is it symmetrical? No, it isn't. So that means it has dipole-dipole. The hydrogen's attached to a fluorine, oxygen, or nitrogen. Yes, indeed, nitrogen. So this has hydrogen bonding, but it only, I'm going to put a times 1 there. Okay, because the nitrogen only has 1 lone pair. It can only form a hydrogen bond with 1 other hydrogen in a neighboring ammonia molecule. Okay, so it can only form 1 hydrogen bond at a time. All right, next molecule, HF. So similarly to HCl and HI that we just drew above. Whoops. All right, so fluorine, this is hydrofluoric acid. Okay, so there it is. Obviously, it's got dipole dot, it's got London dispersion forces, and it also has dipole-dipole because it is not symmetrical. Is this hydrogen attached to a fluorine, oxygen, or nitrogen? Indeed it is. So this is hydrogen bonding. And the one, though, because it only has one hydrogen, so it can only do a hydrogen bond with a single fluorine. Okay. And then the final molecule, CH3F, which you have seen a couple times now. This guy is a tetrahedral molecule, right? It's got LVFs. And it is not symmetrical, right? So it has dipole-dipole attraction. It has hydrogens. Are those hydrogens attached to a fluorine, oxygen, or nitrogen? No, they are not. Okay, so let's try to put these guys in order in terms of highest boiling point to lowest boiling point. Right, so lowest boiling point is the molecule with the least number, or with the least amount of intermolecular forces. Obviously here we can look at all of them, and we can see that the CH3F only has London dispersion forces and dipole-dipole attraction. So that one's we would predict that one to be the lowest. Okay? Now we want to kind of fill things in as we go. So try to pick out the ends, and then we'll work in the middle. Okay, so highest. Which one has the most intermolecular forces? That is correct. That is water. Okay. And LDF, dipole-dipole, and 2 times the hydrogen bonding. Now the middle here, the middle two guys, all right, how can we differentiate these two? They both have hydrogen bonding, they both have dipole-dipole, and LDFs. So they seem pretty similar. Okay. So let's look at these. Is there some differences here? So hydrogen bonding, both of those have hydrogen bonding. They both can form one hydrogen bond. All right, so we're not differentiating there. In the last example, hey, we compared LDFs and their mass. Well, the mass for this guy is equal 14 plus 3, so that's going to be 17. The mass for HF, just getting its molar mass from the periodic table, is 20. Not much difference there. Okay, those are almost the same. So the key has got to be here in the dipole-dipole. Which one of these do you think is more polar? Yeah, HF, but fluorine is most electronegative. Element on the periodic table is the I'm taking my electrons and going home element in a bond. So, yeah, that guy's going to be more polar, so it will have a stronger dipole-dipole attraction than NH3. So HF will be the next highest boiling point, and NH3 will be the next lowest. All right. So there we go. So I hope you feel the last 2 questions here. Number 6 and number 9. Those 2 questions. Those are kind of like AP level type questions. Okay, like 400 plus. All right. You won't necessarily see questions that hard on your quiz. All right. So if you feel pretty comfortable with that, I think and ultimately with all the examples we've done at this point, I hope you do, that you're ready to go for your quiz. So let's make it happen. The quiz should be getting posted automatically up on Google Classroom. You can find it there. And you have the rest of the period to finish up and turn in your quiz on Classroom. People that are in person, if you would like to do, actually, people that are in person, it would be huge to turn your quiz in online. It would be the best option. You do it like you were at home. Okay? All right. And you have all the full resources that you normally have to do. Okay? You can use your computer, you can use all your stuff, all your notes, all that stuff. All right? Okay. Talk to you guys. Have a great weekend, and we'll see you soon.